Hi, this is a video called Creatively Page 51, which is some discussion of Floyd's algorithm. And Floyd's algorithm is given a directed graph, a directed weighted graph, and we'll see exactly what we mean by that in a second. Determine all shortest pairs. Determine all shortest paths from vertex to vertex. So you may have studied Dijkstra's algorithm, which gives, I think, all shortest paths from one source vertex to everywhere else. And that's probably based on the greedy approach, but Floyd's algorithm is designed using dynamic programming. And let's look at it now. So the first thing we're going to need to do is start a new page. Okay, so here's our new page. So the first thing we're going to bring in a graph that I have cunningly prepared ahead of time. So hopefully this will work. Oops. Okay, so here's our graph. Now we're going to resize it and move it over here. Okay, so this is, just line it up. So this is a directed graph. You can see, I'm going to get some arrow thingy here. So you can see we've got vertices. The vertices are the circles, V1 through V4 or V5, and often we'll leave off the V and just write 5 in the circle, or even loosely say that the vertex, just say 5 for the vertex. But and then there's edges, and they're directed edges. You can see they're arrows, not just edges, and each edge has a little weight on it. And those weights are represent the cost of getting from one vertex to another. So for example, we can get from vertex 1 to vertex 2 with just a cost of 1, but the cost to get from 1 to 3 directly is infinity. So there's no edge at all, but we can, just on inspection, we can see that we could get from vertex 1 through vertex 4 to reach vertex 3. So we can get from 1 to 3 at a cost of just 3. So Floyd's algorithm will give us the shortest path to get from any vertex to any other vertex. So, and notice the shortest path from V1 to V1 we'll just always say is 0, of course, because we're just there. And so we'll ignore that kind of step. Okay, so to represent the obvious way to represent a directed graph would be to use references and pointers and objects and make all kinds of crazy stuff, but it turns out there's a much simpler way using a matrix. So so we have a matrix form of this guy. Oops, I didn't cut off the... Okay, so this needs to be smaller. And now, to avoid a lot of cursing, I think I'll put it over here for my own strange reasons. So to avoid a lot of cursing, I'm going, move this guy over a little bit. I'm going to lock these guys, so just a second. Lock it. And I'm going to lock this one. This will keep us from, oops. So now if we try to move these, they won't move. I see I'm learning new things about this explain everything software all the time. So, this let's see, Okay, so the Floyd's algorithm is based on the dynamic programming technique. So each cell of this chart represents an answer to some subproblem, as always. So this guy that we start off with is D0. So in general, we want dk of ij to be the shortest path, actually the weight, total weight of the shortest. It really should be lightest, but we'd use lots of things just meaning the best. Weight of the shortest path from vertex I to vertex j. So that doesn't use the k, using just v1 to vk as possible intermediate vertices. In other words, so the thing we're looking at is this guy right here. This is V0, because these are all the shortest single edge paths. For example, to get from vertex 1 to vertex 5 costs 5. So we look here in row 1, column 5, and we see a 5. The numbers in the bottom we'll explain what they mean later. Okay. And notice to get from vertex 1 to vertex 1 is just a weight of 0, so we'll never change those. All right, so there's a recursive picture that goes with this definition. So we're going to define dk of ij with a picture. Okay, in terms of dk minus 1. So the recursion goes from chart to chart. So we start with the whole chart D0, and we use it to compute the chart D1, and from that we compute D2, and so on until we get up to D5. And D5, if you read the definition, is D5 ij is the weight of the shortest path from Vi to Vj using any desired vertex as an intermediate vertex. So here's the big idea for this. The picture is you have right now in the graph a really clever way called d super k minus 1 of ij. So that is in the dk minus 1 chart, that's the best way to get from I to j using vertices 1 through k minus 1 as intermediate vertices. And what if we're now, so one good way to get from I to j using vertices 1 through k as intermediate vertices would be to not use vertex k. But if we do use vertex k, then we can travel some path till we get to vertex k, and then from there we could imagine going back on to vertex j. It's not a very good j. So now to make the recursion work, we just have to figure out what label to put on this edge here. And in fact, the label we want is d k minus 1 from I to k. So that says what's the cheapest way to get from vertex I to vertex k, I to k, using just vertices 1 through k minus 1 as possible intermediate vertices. And similarly, this path is dk minus 1 k to j. So there's two paths that are of interest here. One is the direct path, or not direct, the one that uses the stuff we already know. It's like, hey, there's going to be some nice way to get from vertex I to vertex j without using any of the vertices k on up. But now we're allowing ourselves the use of vertex k as we move from chart dk minus 1 to chart dk, and that will let us maybe do better. And we'll do better if this plus this beats this. And that's all there is to Floyd's algorithm. So let's try to apply these ideas on our chart. So we start with D0. And on D0, to move to D1, I'm going to take a very vivid arrow here and draw it. So what we use is this row and this column. So these are the special row and column to compute D0, D1 from D0. So what we do, and I don't want to make too many marks on the graph because it becomes insanely complicated, so I'm going to try to just use these little guys. And so I'm going to use a different color arrow for each stage, mostly. So we'll use red for this stage. So first thing is we're always going to skip the diagonals, and on this stage we don't look at any of these guys. So none of these can be improved. If you look at the definition, you can't improve. If we're just going to allow one as an intermediate vertex, we can't have it as the destination. These are the destinations. The starting point or the stopping point. So we got to stay out of here. So we're basically just looking at this grid of cells, and we're skipping the diagonals. So there's really just this one, 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 this one. So there's 3 on each row. So let's start with this one. Tricked you. We skipped that one because it's already at 0, so no point in looking at it. So 3. So right now this says using no intermediate vertices, it costs 3 to go from vertex 2 to vertex 3. So the spot in the table gives you the ij. So I here is 2 and j is 3, and we're thinking about using 1. So we're thinking, would it be better to go from vertex 2 through vertex 1 and then to vertex 3? Well, what would that look like? That would look like vertex 2 to vertex 1 costs 9, and then to go from vertex 1 to vertex 3 would cost infinity. So that would be 9 plus infinity, which is much worse than 3. So this guy is better. So it's actually better here to go from I to j without using vertex 1. Just use the direct edge, which is actually where? 1 to 2 to 3. Yeah, so we can go from 2 to 3 at a cost of 3 and then without going through vertex 1. Going through vertex 1 would be a really bad idea. Okay, so that one is done. Now what about this one? Well, the 2, so what we're comparing, it turns out, if you think about this a few times, 2 to 1 is 9, and 1 to 4 is 1, so it costs 10 to go from 2 to 4, and you can verify that. 2 to 1 is 9, and then 1 to 4 is 9, one more, so that's 10. And whereas the direct route is 2. So the chart gives us all this information, and we can very quickly and easily do that. All we do is, I'm going to do this once. All we do is, just to demonstrate, when we're thinking about changing this, we look up to the special row and over to the special column. So it's column, this row, and this column that are special. Okay, now I'm really hoping, and we add up these two numbers to see if they beat this number. And if they do, well, yay, but that hasn't happened yet. So I'm really hoping I can undo those. So I don't want to manually erase them. Okay, now, so the 2 didn't change, but now we're looking at this guy, infinity. So the infinity, we got 9. So going from 2 to 5 directly costs infinity. You can't do it, basically. But if you go from 2 to 1, that's 9. And from 1 to 5, that's not 5, so that's 14. So 14 beats infinity by quite a bit. So we cross this out and write 14. And, this is important, in order to be able to figure out our path later, we write 1 there. It's the intermediate vertex that you use to get that done. Okay, so now moving on, we look at this infinity. So this infinity, we look here and here. And whoops, there's an infinity there. So if there's an infinity in the special column or row, you don't even need to do the calculations. You're not going to improve. So I can take care of, because of this infinity, I can just swoop past, ignore those. None of them are going to work. Okay, so let's undo this. Dotted lines are bad. Okay, carefully not going too far back, I hope. Okay, so now we move to the next row. So this also has an infinity. So nothing's going to change on that row. And now in this row we have a 3. Ooh, so this is going to be juicy. Because, so this infinity here is beats by 4. So we cross this out and put in 4 and 1. Now, but this infinity doesn't, because of this, when the value in the special row is infinity, so there's not going to be any improvement. Okay, and but this infinity is improved by 3 plus 1. So we cross it out and replace it by 4 and by 1. Okay, so that's the end. This is now D1. So this chart now gives all the ways, the best ways to get from any vertex to any other vertex where you're allowed to go through one intermediate vertex, namely just vertex 1. Okay, so now we're ready to go from D1, which is the current chart, we're going to advance to D2. So to do that, we're going to rub out these special marks and put in the next special mark. So now it's row 2 and column 2 that are special. So we somehow have to keep that in our heads. Okay, and let's go for it. So every other cell, and there's 9 of them it turns out. There's 4 other rows and columns, but there's only we skip the diagonal. So we look here. So can that be improved? No, see, I tricked you. This is in the special row, so we don't look at it. All right, how about this guy? Can it be improved? Well, so we look down to the special, we look over to the special column. It's easier to do with 2 hands, and down here. So in fact, that can be improved to 4. And again, and I'll stop rehashing this because it really is just this one picture. To get from 1 to 3 is impossible right now, but this picture says go from 1 to 2 and then go from 2 to 3. It's our total cost of 4 if you're allowed to go through vertex 2. So let me just go ahead and do that. So this becomes improved to 4, and the intermediate vertex to use is 2. Okay, how about here? So what we do, let me try to do this with the arrows. What we do is we're focusing our eyes on this, and then we need to take our left hand and look straight sideways to the special column. So you go over horizontally to the special column and see a 1, and you go down till you see the special row. So we're comparing 1 plus 2 is the indirect path that goes through 2 to 2, so no improvement. Okay, how about here? This is 5 versus, so already we don't even have to look over here. So the indirect path costs 15, but as soon as we see we're going to lose, we can move on. Okay, now do we go here? No, because it's the special row. So we just skip down here. So infinities are fun. So we look for infinity. Can we improve that by going through 2? So this says could go directly from 3 to 1 is impossible, but maybe we can go from, let's see, yeah. So maybe we can go from 3 to 2. Oops, that's it. So that's an infinity. So the infinity here in the special column means we can't improve any one of these three guys. And same thing here. This infinity means we can't improve any of these. And now the 4, so the 4 is already worse than the 3, so that's no good. And now what about this one? Aha! This is 4 versus 3. So in fact, this can be improved to a 7. So let's do that. Let's see, I guess, am I still on? Yes. So this becomes 7, and that's going through vertex 2. So it says to get from 5 to 3, we can go 5 to 2 to 3. So 5 to 2 costs 4, and 2 to 3 costs 3, so that costs the total cost of that path of 7. Okay, and then this 4, now we move on over and look at this 4, and we compare it to the guy in the special. So it's already a tie, so it would be 6 indirectly, so we can't improve that. So we are now done with we're now looking at the chart for called D2, meaning we're allowed to, where it's the shortest paths from anywhere to anywhere else, using vertices 1 and 2 as intermediates. So there were two guys that improved on that level. This one and this one. Okay, and we still haven't seen, they can stack up. So both of those only weren't using vertex 1, but later we'll see at least one case, I think, where it stacks up. Okay, so now what do we do? So now we're moving on to vertex 3. So we rub out the specialness of the second row and column, and instead we're going to go to the special third column and row. Okay, so we just scan the whole matrix, and by the way, if you think about it, this is a theta of n cubed algorithm, the efficiency. It's an n squared grid, and we go over it n times. We look at almost everyone. If n were 100, the fact that we're skipping the diagonal and the special row and column would be negligible. Skipping 2 out of 5 is a big deal. Skipping 2 out of 5 is a big deal, but skipping 2 out of 100 is of course not. Okay, so using the green here, let's go through. So do we look at this one? No, it's on the diagonal. Do we use this? Yes. So shooting your eyes sideways from here, you shoot over to here, 4, and as soon as you see a bigger number, you stop. Okay, skip the special column. Can't improve that. Oops, so this 5 could be beat by 4 plus, infinity. So none of those changed. On to row 2. So, infinity, skip it. What am I doing? Oh, I'm in the special column. I was trying to find, never mind. 2 beats 3 already. What about 14? 14 infinity. So none of those change. Skip this whole row because it's the special one. All right, how about this infinity? We're comparing that to 2 plus, infinity. So infinity won't improve. Skip the special column, skip the diagonal. So this 3 beats infinity, so we're down here. So infinity, special column, tied already, and so that seems a little strange, perhaps a little disappointing. And what am I saying? What I'm saying is nobody improved. Adding in vertex 3 as a possible intermediate didn't help a bit. Oh well, so too bad for that guy. So now I'm going to rub this out, and since we didn't use any greens, let's use green for the next one. making these so thick, just to highlight that you really want to see them. In the past, I've like made a vivid mark through the whole row and column, but that's hard because then you can't tell which big vivid row or column mark you're using. Okay, so now we're ready to swoop ahead. Oh, so by the way, that was D3. So we're now sitting and looking at D3, and we're ready to go on to D4. So what do? Same thing. It should be getting really boring by now. So skip it because it's on the diagonal. 1, so infinity down here means we don't have to do anything in that column. So 4, so however you feel like doing this. Okay, so 4 could be, this 4 could be beat by 2 plus something. 2 plus, it is, how exciting. So in fact, this 4 can be beat by 3. And the vertex that does that is vertex 4. That's exciting. How about the 1? The 1 loses, whoops, oh, I'm in the special column, damn it. Oh, sorry. Okay, so what about the 5? The 5, 3 plus, where's this? 3 plus 1. So the 5 loses to the 3 plus the 1. So by using our intermediate vertex 4, we can improve that to 4. Okay, next row, so 9, shooting our eyes to the right places, is 2 plus, and oops, infinity. So skip the columns where there's infinities on the special row. So the 3 here loses 2 plus, where am I going? 2 plus 2. Yeah, so the 3 barely beats the 2. So this 3 sideways to the special column is 2, down to the special row is 2, so we don't change that because it's 4. And we skip this because it's a special column. And how about 14 is 2 versus 3? Aha! So we replace this with 5. And we mark here that, what? I don't know why that was marked out. I must have rubbed it out. I think that 14 used to be a 1, but it's now changing to a 4 anyway. Okay? Alright, and moving on, this row, okay, now the infinities we think we can for sure fix, but they're infinities in row, the special row, so those don't get better. So that's the special column. So, but this infinity, so let's see. So what about this guy? It is 3 plus 4. Yeah, so this changes to 7. 7 and 4. Okay, and now we skip the special row. And we look here. So can 3 be improved? No. 4 be improved? No. 7 be improved? Ooh, 2 plus 4. Yes, just barely. So the 7 here is improved to 6 using intermediate vertex 4. And now, what about this 4? Can it be improved? That'd be, oh, it's special column. Okay, so we're done. So this is, we've now, oops, it's not a pencil. We've now got up to D4. So what we're sitting there looking at is D4, and thank goodness we only have one more thing to do. So even though it doesn't show up at all, I'm going to use yellow. And let's see, let me mark this out first. So we're going to use, we're now on to the last row, and last column is special, which is easier to picture. So in this one, we're going to be trying to update all of these guys. Okay, so we just cruise. So diagonal, no. 1 and 4, no. Here, so that one can't be improved. This 3 beats 6 already. The 1 beats the 4 already. Now we're in the special column, so we're just staying in that upper part. So 9, so 9 versus 3 and 5. So yes, that can be changed. So the 9 changes to 8. And that happened on vertex 5. Okay, back to the arrow, so we can't, that's, all right, 3 already beats 5, 2 beats 5, oh, infinity is 3 plus 7, so this infinity changes to 10, and we did that at step 5, vertex 5, and while I'm at it, this infinity here changes to 4 plus 7. Is 11. Skip this guy. 4 loses. Skip that guy. The 4 already beats the 4. And we're done. So now we're down here. So infinity is 3 plus 3. So that is 6. This guy is gonna be replaced by 7. And this guy already, the 2 beats the 6. Skip it. So we are done. This is now D5. So D5 gives the final answers to everything. And you notice over here, this is, just to keep it small and simple, that not too much exciting happens. But here was a place where at one point we thought we could do better with vertex 1 as an intermediate, and then later we used vertex 4. So that happened down here too. We did 2 and 4. So in principle, if you could rig these to have lots of changes happen. So this is a pretty nice example because there's quite a few changes. Of course, there's some places that don't change because the direct edge was just too good to be beaten. Okay, so that concludes that little demo, which is good because this is a ridiculously long video. But there's one last thing we have to do. I don't have space to do it. Let's see, can I drag? Oh, I locked them so I can't drag them. Okay, so I'm going to do something terrible, perhaps. I'm going to rub out this whole area. No, I'm not. It'll take forever. All right. Oh, I know what I can do. I'm going to use the selector. Yikes, don't want that. Never mind. I'll just stick to the poor eraser. Oh, it's for some reason bigger. I don't know how to make a bigger eraser. All right, just take a moment to do what we need to do. All right, so one last important issue is the, whoops, I went black. So we want to get the optimal path. So let's pick an interesting one. Let's take the optimal path from 2 to 5. So the optimal path from 2 to 5, let's see what's going on with that. So we look at the chart and we just do it recursively. So this cell says the way to get from 2 to 5 is you go through vertex 4. So that tells us in the first step that we know we want to go to vertex 4. And then we simply refine each of those paths. So we look for 2 to 4 is this cell, which is simple. So we're done. That's just a direct edge from 2 to 4. So So we start at 2 and go to 4 directly. Can't beat that. And then to get from 4 to 5 is also simple. So the direct path of size is 5, and it goes through 4. Let's see if we can find a more interesting one. Maybe not. Anyway, that's the idea, is you just keep looking at the chart and understanding exactly what the information in each cell tells you, and you can refine each of the subpaths with another intermediate vertex until you're done. Let's see, what about 5 to 3? 5 to 3 goes from 5 to 4. All right, yeah, let's do this. One more example. I should have prepared a better one. So what's the optimal path from 5 to 4? So the best path from 5 to 4, and we look at the chart, 5 to 4 goes through the intermediate vertex 1. So we know it's 5 to 1, and then to 4. And we know that, okay, and then 5 to, what? 5 to 1? Oh, you know, I wanted 5 to 3. Sorry, I'm going to undo. Oops. Okay. I think 5 to 3 is better, so you go from 5 to 3, that's this cell. 5 to 3 goes through vertex 4. And then 5 to 4, that's why I wanted at least one improvement. 5 to 4 is here, and that goes through vertex 1. So 5 to 1 to 4, and then 4 to 3 is just a simple one. So that's our optimal path. And if we look back up here, let me use a different color. So we start at vertex 5, and we go to 1 at a cost of 3. And then we go from 1 to 4 at a cost of 1. And then we go from 4 to 3 at a cost of 2. For a total path length of 6, which is what we had. Okay, so that concludes the video on Floyd's algorithm. So now you should be ready to do your example routine exercise asking you to do the same thing with different graph, and then if you choose to, the project 5, which asks you to implement this. So this is really, to program this all up is really quite a simple thing. Thanks.